We're going to continue with where we left off about the neutral point and the static margin, which we need to define today. So where we left, we had gone through and calculated the total pitching moment, split it up into stuff that multiplied angle of attack and stuff that didn't. The stuff that multiplied angle of attack we called Cm alpha, and that's the stability parameter that we look at for pitch stability. And we talked through how by making this distance small enough, and making the tail or the distance big enough that we can make the whole thing negative because of that minus sign. And then we said, well, there's a certain CG position that makes neutral pitch stability. So Cm alpha is 0, so you don't get any pitch up or pitch down due to an angle of attack change. In other words, there's no tendency to return back when there's an angle of attack disturbance. And so we want to know, well, where is that CG position so that we can keep the neutral, we can keep the CG in front of that position on the airplane. And then we took the formula for Hn, which we got by saying this thing equal to 0 and saying that's Hn, and we solved for it. And then we were able to eliminate the stuff in this formula by substituting with the appropriate sign. And then we got a simple formula for Cm alpha, if we already knew what the neutral point is from this formula here. So you'd think, well, that's a simple formula. Well, there's no shortcut in the calculations. You either do this part of the calculation down here and get Hn and then put it in there and do the rest of the calculation, or you use the total formula here. It's just the same amount. It's just whether or not you've already Hn. But this does allow us to say, okay, for Cm alpha to be negative, that means H, the CG location, has to be bigger. Oh, sorry, the other way around. Hn has to be bigger than H, right? So if this one's big, the minus sign means we get a negative Cm alpha and it's stable. And so we call the distance between these two the static margin. So we're going to define that in a minute. So let me give you a minute to finish copying down on this, and then I'm going to switch over to the other board. So let's draw a picture of what's going on. Here's the datum. Here's the center of gravity. And if the neutral point is aft of the CG, then this distance is bigger. And then this distance here is the difference between the two. And notice that that's the flip of the formula that we have for Cm alpha. So it's just geometry. It's this distance minus that distance gives that distance, and that's what shows up here. And so we call that the static margin. So that distance in fractions of c bar is called the static margin. And it literally is the distance in fractions of c bar that the CG is in front of the neutral point. Just looking at the picture, that's what it is. And so often people will quote stability for an airplane not as Cm alpha is negative 0.4, because what does that mean on the airplane? There's no physical measurement that's just Cm alpha. But if you say, hey, this distance, the static margin, is 0.1 c bar, then you know where that is on the airplane. And you know, you calculate the CG on the airplane, you know where the neutral point is, and then you can tell whether it's in front or behind. So there's different equivalent ways to talk about pitch stability. The number one fundamental one is that Cm alpha is negative, because that's saying if alpha increases due to a disturbance, we get a negative pitching moment to restore it back. And that goes back to the fundamental definition of stability. A disturbance from equilibrium causes something in the direction to restore it back to equilibrium. So that's tied directly to the definition. But based on our calculations, we've also found out that equivalent is that H, the CG must be in front of the neutral point. And a direct measure of that is that Kn, which is the difference, must be positive, which says the CG is in front of the neutral point. So this is the fundamental definition. These are more practical ways that we talk about the location of the CG with regard to stability. All right, and picture-wise, on this picture, what it means is the net lift of the airplane acts at the neutral point with this pure couple. Just like when we did an airfoil, we said, okay, at the aerodynamic center of the airfoil, that's where the net resultant lift acts, and we get a pure couple. And then we built the wing, and the aerodynamic center of the wing is where the lift of the total wing acted, and we had a pure couple. This is where the total lift of the whole airplane acts, the net resultant of the wing plus the tail, and we get a pure couple. And you can see why Cm alpha is 0 if we move the CG back to here. Because then you're taking moments about that point, and if alpha increases and the lift goes up, there is no change in the moment. Right? So Cm alpha, the change in Cm with respect to alpha, if you put the CG at the neutral point, is 0, because that's where the net lift acts. So we've been doing a lot of symbols. I want to show you a couple examples. We'll take a Cessna 182 and some data for that and calculate numbers to go with this stuff. But the first thing I wanted to show you is a spreadsheet from a guy, a former student a long time ago. I think I was spelling his name right, Todd Rotramel. He worked for FedEx while he was going to school here. In fact, he went to school during the day, saw his family in the evening, and then worked midnight to 6 a.m. out at the airport for FedEx, and he was their load manager. He was in charge of what and how much weight got loaded in the different cargo compartments on the airplane, and he had to calculate the CG location of the airplane to verify that the airplane was going to be stable before it took off. And he gave me some spreadsheets. Since he gave these to me a couple years later, he said that they automated it with some Excel spreadsheets. But these are interesting to look at because for every flight, he was required to fill out these sheets. So let me share that screen with you guys. I know the Zoom people can see it. You guys can see that well up there as well, right? Okay. So this is the first half of the page, first spreadsheet. And so what he did was he looked at this, and these are cargo compartments, 1, 2, 3, 4, and they're on the upper part of the airplane. And then there's lower cargo compartments, F1, F2, F3, A1, A2, A3. And they have numbers associated with them, which are really fuselage stations. Where are they located on the airplane? And what he did was he looked up the weight that was located in each cargo position. So these are the lower cargo here. He'd look up the weight in the yellow and then go across and add or grab the number that's called an index here, which is really a short, not a shortcut, but a simplified way to calculate weight times moment arm for the location of that particular cargo. So these indexes then go to the next sheet. And you can see that they give formulas here where it's weight times essentially a moment arm, and somehow it's adjusted for an origin here with 1,000. But it's weight times moment arm is essentially what they're doing. And then here's the same thing for the upper cargo. So each of those cargo holds, you'd look up how much weight was in there, go across and grab an index, which was weight times moment arm. And he even did that for the fuel tanks. Each fuel tank had so many gallons of fuel in it. That generated a moment arm index for that. And it is detailed enough that if there are additional people up in the cockpit in the jump seats, they add in an index based on that. So they assume 2 jump seaters weigh about 200 pounds each. So that gets added into the whole calculation of the CG of the airplane. Now this is a cargo airplane. For passenger jets, they have to do that for the seats that are filled in the jet and guessing at how much each person weighs. So then that goes into the next sheet here where he's grabbing all those weights and indices and putting them in this spreadsheet to go down and calculate some totals here at the bottom. So he has a total of the upper compartments, total of the lower compartments, both weight and index, because he has to know, well, how much does the airplane weigh, so he knows if it can get off the ground for takeoff, but the indices tell him whether he's stable or not. And they do this for 0 fuel weight and takeoff gross weight and ramp gross weight, because Obviously, it has to be stable on takeoff, but near landing, when it's used up most of its fuel, he has to know that it's still stable. And you can see this is one he actually filled out. It's for a flight from Wichita Mid-Continent, or Eisenhower now, to Memphis, which was a hub for FedEx. And all of those indexes give him numbers that he plots on this. Here's takeoff gross weight, location, aircraft index on the bottom, aircraft gross weight on the vertical axis. So that's the crosshairs for that. And then here's if all the fuel is burned, the CG shifts. And he has to pay attention to both a forward limit for takeoff and an aft limit. Now the aft limit makes sense, right? Because we've talked about if the CG is too far aft, it becomes unstable. The forward limit has to do with elevator power and the ability to do nose wheel rotation on takeoff. So what we're talking about in class is fundamentally critical to the ability of the airplane to fly and stay flying in the air once it gets off the ground. As we go through the Cessna example, you'll see that the margin between the nominal CG and the neutral point is pretty small. So you could get to the situation where shifting the CG slightly in a Cessna could make the airplane unstable. So we're going to calculate these locations. This is a picture, a top view of the airplane. I guess I need to share that. So we know the geometry of the airplane. We know the wing span, wing chord, wing location, the location of the aerodynamic center of the wing, the location of the aerodynamic center of the tail. We'll have actual numbers for that. Plug them in these formulas and calculate the neutral point and various other features of the pitch stability of this airplane. We'll find out that this distance between the nominal CG and the neutral point, I think, is about ½ a foot. So it wouldn't take too many heavy suitcases behind the seats back here, or even in the seats, to shift the CG back and cause the airplane to be unstable. So here's our example. So it's a piston engine, approximately a Cessna 182. I'm not saying it is a Cessna 182, because then you might get in one and do some calculations and crash and sue me because I said, hey, this is a Cessna. These are approximate numbers anyway. So the wing area is 174 square feet. The wing mean aerodynamic chord is 4.9 feet. The tail, 30 feet squared. The distance from the aerodynamic center of the wing to the tail, that's LT bar, 14.3 feet. And the tail setting angle is 2 degrees. And the downwash model has epsilon 0, 0 and d epsilon d alpha of 0.3. And then we have Cm AC of the wing body, so that's the pure couple. the wing. The propulsion, we're going to say we can neglect. Thrust line is pretty much through the CG. The weight of the airplane is 2,645 pound force. The CG is at 0.390 times C bar, so H is 0.390. And we know where the datum is. This is reference to the leading edge of C bar, and since the wing is almost rectangular, that means it's the leading edge of the wing. The lift curve slope for the wing has been calculated with something like the big formula, and so has the tail. And the neutral point of the wing has been calculated. That's essentially X bar that we get from Appendix C. So we calculate X bar for this, and that gives us the neutral point of the wing body. I'm sorry, yeah, the right, the neutral point of the wing. Okay, task number 1, where is the neutral point of the whole airplane? And then what is the static margin? And then we'll do some other calculations. We'll calculate Cm0 and Cm Alpha, just to show you how, although some of these formulas have a lot of terms in them, if you know everything about your airplane, you just get numbers that go in there. Okay, are we good over here? Is anybody still writing? You're still writing? Okay. You guys are my test subjects that tell me whether the Zoom people are caught up. You ever watch a TV show on CBS called Bull? Anybody watch that? It's about a lawyer who's a PhD in psychology, and he has a team of people that for a jury trial create simulated jurors that model, or they call them mirror jurors. They model the jurors that are actually on the jury, and they try to predict how the juror, each individual juror, is feeling and interacting and reacting to the evidence presented. So you guys are like my mirror students, although you're really here. Anybody else still writing? Sorry, I was killing time there. It's a good show. If you like to watch TV, look it up. It's called Bull, B-U-L-L, on CBS. I think it's on Monday nights. Okay, I'm going to shift over here. More rambling while I erase. The reason I got hooked on the show is my brother-in-law lives in Colorado, Missouri, and one of the stars of this TV show showed up in his grocery store in Colorado, Missouri. And he had been watching the show, so he took pictures with him. It turns out he's from Southern Illinois. Just goes to show if you're a manager of a grocery store, you never know who's going to walk in the door. Okay, we want to find the location of the neutral point. Gosh, more rambling. I think I have the name right. Do you guys know who Joe Walsh is? Guitarist for the Eagle, right? Pretty sure it's him that grew up here in Wichita. One night, a house down in Riverside, they got their doorbell rang. They opened it up, and Joe Walsh was there with a couple other famous people. It was his boyhood home, and they just were in town, and he stopped by and rang the doorbell just so he could look at his house. Imagine that. All right, so we want to find the neutral point location. So we go to our formula that we calculated for this. And there it is. So we look, what do we have and what do we need to calculate? Looks like we got AT and A on the previous screen. We have d epsilon, d alpha. The propulsion stuff we're neglecting. Looks like we need VH bar. Because we have A wing body and we have AT but not A. So A, we go back to where we defined the lift curve slope of the entire airplane. This was when we were adding the lift of the wing plus the lift of the tail together. And then we separated everything out into the stuff that multiplies alpha and the stuff that didn't, and that was the A, is the stuff that multiplied alpha. And we look at this and we go, well, we know all this. We know the wing area, we know the tail area, we know the lift curve slope of the tail, we know the lift curve slope of the wing body. So we can punch numbers for this. All right, so let's break things up. You guys have the numbers, right? So pull out your calculator and give me a number for that. And then VH bar is LT bar over ST over C bar S. You guys on Zoom, calculate it and type it into the chat. Yeah, so somebody confirmed on the chat that Joe Walsh was the one who was raised in Wichita. The story I remember was that he showed up with, I think it was Eddie Murphy and somebody else that was famous. And don't be shy, just shouting out numbers when you get them done. Sometimes you'll be right, sometimes you'll be wrong. It's no big deal. This is just practice. Especially with that big formula, it's easy. We found out it's easy to make mistakes, right? What's VBRH? This number sounded big. What did you get for that?
18.21. I got 4.4.
Yeah, the 18, and you can see why I'm suspect of that, right? Because the lift curve, the ideal lift curve slope is 2 pi. So what are you getting? 4.41? 4.424? Okay. And what's the units on that? Yeah, because everything else over there is per radian, right? So everybody, guys on Zoom, are you guys confirming this? Yeah, somebody said 4.42. Oh, lots of 4.42s. And the VH bar we're good with. Let's see if that matches. Yeah, so we're good there. Any questions about that? All right, so then we go up to this formula up here and calculate Hn minus Hn wing body. So that's going to tell us the distance from the neutral point of the wing body to the neutral point of the entire airplane. And the propulsion stuff's 0, right? So how we did on that? .2787, I see 0.279, 0.2789, 2.2787. What are the units on that? None. Correct answer is none because that's in fractions of c-bar. So if we wanted an actual distance, we have to multiply by c-bar, which is 4.9, and you get 1.36 feet. So what distance on the picture are we talking about? We're talking about the distance from the aerodynamic center of the wing, which is this line, back to the neutral point of the airplane. So that's the distance. Now we can calculate the static margin because we were told where the CG is, so let's do that next. So the static margin Kn, Hn minus h, it's going to be positive if the neutral point is behind the CG because that distance is going to be bigger. And we didn't actually get Hn, so we've got to do that first, don't we? So Hn minus h and wing body is 0.2787, and we know this location, so we have to look that up. I lost it on my sheet. There it is. It's 0.25. And so you can calculate Hn as 0.529, or you multiply by c-bar, and you get 2.59 feet. And you got feet from where? This is aft of the leading edge, because this is our datum. It's aft of the leading edge of the mean aerodynamic chord. So once we've got that, then we can plug that here. And the CG location we were given, right? Yeah. CG was 0.390, again, reference to the leading edge. So both of those are reference to the same axis. So then Kn is 0.139. So I'm subtracting, does that look right? 539 minus 0.390 looks good. If we want feet, we've got to multiply by c-bar because it's all non-dimensionalized. And we find out that the distance that the CG is in front of the neutral point is only about a little over ½ a foot. And since the whole airplane only weighs 2645, if you put 500 pounds of cargo in the back part of the airplane, you could shift the CG on the wrong side of the neutral point. So you do have to be careful about where people sit in the airplane and where you put cargo, and there's a limit to that. That's all in the pilot's handbook. Okay, for some other stuff, let's calculate Cm0 and Cm alpha from the straightforward from the formulas. Can I shift over to the other screen, the other board? You guys done with that? Are we caught up? So the next formula we need, first thing, do that, we're going to calculate the alpha to alpha wing body relationship. Remember, it's just shifting the axis of our lift curve slope axis. So alpha is the airplane angle of attack. This is the wing body angle of attack, and the formula for that. We don't really need this. I just want to show you that it is a simple, just a number added to the axis based on the geometry of the airplane. And there's a key feature here. What do we put in for these numbers? We had epsilon 0 was 0, and IT was what? What did I list it as? So I said 2 degrees. So if I put degrees in there, then I've got to do all my angles in degrees, right? Because the units here are degrees, the units here are degrees, because areas, units cancel out. These units cancel each other, they're ratios. So if I have degrees here, I've got to use degrees and degrees, right? I'm going to do it in terms of radians. So that means we need to multiply this by pi over 180 to go in there. If we plug all the numbers in for that, and since I converted to radians, this is in radians. So you can see that even though it seems, well, gosh, we got alpha, we got alpha wing body, it's just a shift of the axis by this number here. All right, now I'm going to have you guys calculate Cm0. I'll put the formula up here. We're going to need all these numbers again. So Cm0, and here's what we're calculating. Remember, we collected everything together in terms of the stuff that multiplies alpha and the stuff that doesn't. So Cm0 is the stuff that doesn't. It's a long calculation, so everybody take a deep breath and start working on it. And this is all times this bracket here, so I'm going to write it down here. Looks right. The propulsion stuff we're neglecting, so that's not in there. So start crunching away on that. And then we're also going to calculate Cm alpha. Making you guys work today, huh? And then the propulsion stuff is 0. So let's give me a number for Cm0 and a number for Cm alpha. And that'll be the last thing we do today. How's our time? 11 after? Okay. I see a Cm0 of minus 0.1004. I'm running out of room. Let's go over there. That was on Zoom, by the way. So you guys have a number for Cm0? I've got a number different than minus 0.1. 0.211? 0.07? There's a lot of terms in here. Let's make sure I wrote the formula right. This is CMAC of the wing body. I gave you that number, right? AT, VH bar. We calculated that. We got that right. AT was given. Oh, what are you doing for this? You're putting in 2? Yeah, so you've got to convert this to radians because this is all in radians here. So this is 2 times pi over 180, right? Anything else? We calculated A, we verified that. ST is 30, 174, d epsilon d alpha is 0.3, right? I get a number of 0.04. Did I? You guys are validating that? Okay. Now how about Cm alpha? I'm getting 3.6. Did you guys get that far? Uh, 4.42 for A, 0.39, 0.25, 3.5, 0.503, 1 minus 0.3. And in fact, there's another way we can check Cm alpha, isn't there? Because we already calculated the neutral point. And Kn, remember this is just the negative of Kn, that H minus Hn. And so we plug in 4.42 that we got for that, and we plug in minus 0.139. Kn was 0.139. We get minus 0.614. So indeed, you can calculate the stability multiple ways. Calculate Cm alpha straight from the big formula. Negative, stable. We've already calculated the neutral point. You can calculate Kn and then calculate Cm alpha this way, or you can just look at the value of Kn and say, hey, it's positive, so it's stable. Either way, that static margin was what? It was like, yeah, it was a little over 1/2 foot, right? That we need to shift the CG. So if I ever ask you a question, if I gave you an airplane and said the static margin is 0.139, what would you do to make the airplane unstable? Your answer would be put some weight on the tail, right? Or vice versa, if it's unstable. Hence, sometimes when you make a paper airplane and it wants to pitch up and flip, you put a paper clip on the front that gives more weight to the front, moves the CG forward, and helps stabilize it. Questions? We'll stop here with this example. Looking at questions on the Zoom. So I think we're good. You guys have all found the homework that you're working on, right? This used to be a longer homework, and I've chopped it into 2 parts. That's why it's called part 1. So you go through and do some calculations, and then the second part, you're just calculating numbers for some distances and values, just kind of like what we did here.